And I'm gonna talk about like partly about my PhD thesis about how to do precise photometry and astrometry for exoplanet imaging. Generally, from the exoplanet position and flux measurement, we can measure or we can define the orbit, time period, or mass of the planet, or study their mean temperature or planet spin or atmosphere from just by measuring the flux and signal from the exoplanet light in coronagraphic images. But in post coronagraphic image, the central starlight is generally blocked, and we don't have any on sky reference to calibrate the planets. And it's hard to monitor the fluctuation in the planet signals with time. And generally, for this, we create a satellite spot uh, by by applying a phase grid.
Sahoo?
Generally, hello.
Oh, yeah. Maybe you could switch off your camera because the sound is not very good. So to improve the bandwidth, maybe you could do that. To switch off just to leave the share screen, but to switch off the video.
Let me do.
Is it possible?
Yes.
Okay, maybe it will improve the sound. Thank you. Sorry for the
Okay.
interruption.
It's okay. So what we do is add a face mask and in the people plane and make satellite spot in the focal plane. Generally, the first term is like the central PSF, and this third term, what we get out of the Fourier transformation is for the two satellite spot, which are copies of the central point spread functions. And in on sky images, here I just want to see the satellite spot like vary with the frequency of the grid and amplitude. So mostly we can place them at any point in the focal plane just by adjusting the frequency and amplitude of the sine wave phase grid that we apply. So generally, what happens in on sky that the satellite spot they they interfere with the underlying background speckle and form some other copies of the starlight which are not actual phase. So mostly uh, this interference term consists of the actual intensity of the satellite speckle and then the background halo and then the mixing of the speckle spot with the background spot. So so what we finally see is that the uh, actual intensity and position of the satellite spot is affected by the underlying background halos phase and intensity or strength, I would say. So we do like a 2 times temporary correction. Oh, sorry. No, no. Uh, so mostly what we do is to like switch the phase of this speckle spot between like 0 and pi at high speed to remove this mixing term. And here is what we get the actual like the
Sahoo?
variation of the intensity. Yep.
We don't see your slide anymore.
Oh.
I don't know.
Uh, uh, I again started screen sharing. Is it visible to you now?
Nope. No.
Okay. Um, again, I
Yeah.
sorry. Again, I started screen sharing.
Yes.
Uh,
Perfect.
It's good.
Perfect. Very good. Thank you.
uh, so generally, the satellite spot is what at the end, like after switching the phase at high speed between 0 and pi, we get like a mixture of this incoherent uh, background and actual intensity. So to finally remove this incoherent background speckles, I do like alternate the spatial position. Generally, to first I kind of generate the incoherent satellite speckle for one frame and switch the spatial pattern between frames, and by subtracting two frames, I kind of arrive at the actual copies of this central star. So I implemented this this method on the with the SCEXAO instrument at the Subaru telescope. So by making a time synchronization between the science camera and the SCEXAO's real-time computer, what happens is that uh, as soon as a file is seen by the science camera, the spatial pattern is synchronized. At the end, we get something which is similar like this for the entire observation sequence, like spots, incoherent spots in one frame, and the spatial pattern switching between frames. This kind of back and forth. And with this, I took some data with like type of faint grid and a brighter grid. So in both the cases, we can see that the satellite speckle is buried under the residual speckle halo in case of the fainter grid, and in the brighter, which is roughly 10 times brighter from this one. Um, and by subtracting these two close frame, we can see arrive at like more good copies of the point spread functions. And I measure how the intensity and variation of this, how the intensity or the position of this copies varies with time. I see a very clear improvement in photometry and astrometry. So the first green curve in this images is what a regular person would like achieve just with the regular satellite spot with no modulations. But the mm, bottom curve is what one can get when they use this alternating method. So for a time of like 1 hour our integration time, I see an photometric like improvement by 2 times, and an astrometric measurement improvement like from like 3 milliarc second to like 0.2 milliarc second. So it's a huge improvement, and it would be really applicable to do like time resolved precise photometry on sky. So here I analyze the major sources of noise in my photometric and astrometric measurement. So from this table, I see that the speckle noise is the main source as compared to the photon noise and readout noise. And flat fielding method that never shows up in my measurement, but still it's like present. So to remove this speckle noise, what I do is like switch the spatial pattern at like more higher speed to remove or subtract the background at really high speed. So for this, I I switch the spatial pattern at like high speed up to like of the order of 1 millisecond. Here are some of the on sky on-sky images I took with the seeded to camera with like a satellite photo, where each spatial pattern was switched at 2 milliseconds. And now this method is kind of validated with SCEXAO instrument, and I received I get a 1% photometric accuracy with also like a very faint satellite grid. And now it's open to astronomer as a part of regular science observation at the telescope. Yeah. With that, I would like to finish my talk. Thank you for patience listening and.
Thank you, Sahoo. So we don't have much time for questions, so I encourage you to ask your questions on the Slack, and Sahoo, you will be able to answer that directly online. Thank you very much for this interesting talk. And so we have now